Okay, so good afternoon, everyone. We'll get started with our afternoon session. And the first speaker of the afternoon session is Dinesh Bharadia. Dinesh is an associate professor at the University of California, San Diego, where he directs the Wireless Communications Sensing and Networking Group. Welcome, Dinesh.
Thank you. I guess everybody can hear me, right? Yeah, okay, good. Okay. So, hi everyone. So let me present something we have been trying for like past 2.5 years, right? I think so we really started with a very simple idea like, hey, there is 4G and 5G already out there and they're open. They're pretty much like doing software programming, right? Or like doing like MATLAB or whatever, right? Let's build some application on top of it, right? And try things out, right? So that's sort of what we started with. And then we realized that we can't build any of the things we are trying to build because we can't optimize and there's performance is not sufficient, right? So this is my agenda going to be, right? So I'm going to maybe dwell into quickly the motivation for what we are trying and then sort of present the architecture of something called EdgeRIC, right? It's a sort of a new RAN intelligent controller, right? Which sort of has a different philosophy than the other RICs you have seen so far, right? There is a near real time and the non-real time RICs we have all seen, right? So that's sort of what is it? Why do we need, right? I will answer that question first. And once I have presented EdgeRIC, then we started trying, can we train some AI-driven algorithms on top of this and sort of deploy them, right? Then we ran into a lot of problems doing that, right? And then we invented something called digital twin, right? And it may sound like same as what others have been presenting, but there is a very unique philosophy of what we were trying to do, right? And what we found basically is that whatever we trained in a repeatable way in a simulation, we deployed over the air and reinforcement learning worked, right? It's sort of over the air reinforcement learning working. At least that was really interesting and cool, right? And again, it was not like we trained it over the air again and again and sort of tried to it. Simulation, it was trained, worked over the air, fantastic, right? And finally, I will tell you about some new things which we are trying to set up, right? Sort of like call it Powder or other platforms, right? We also have trying to create a small interoperability lab. The unique feature for what we are doing is that we are connected to something called Science Network, right? I don't know if you guys know about this. So we have a internet too, right? It's a parallel network and much better than internet, okay? Because you can really get from East Coast to West Coast sub-millisecond latencies and 400 terabytes per second, right? So it's unheard of, right? If you want to try some real cool telemetry experiments, you can do with us, right? You can have a doctor sitting in NYU and doing things in UCSD, right? So that's the third aspect, right? And this is also going to be connected to TAMU as well, right? So it's not to like say just that. And before I go forward, right, I think I am merely a presenter here, right? I think this is a work of all the cool people and there is a demo out there. I don't know if you have seen. If you haven't, please go ahead, check it out. This is joint work with Texas A&M, right? Professor Srinivas Shakota, he's in the audience, right? Wuyun and Ushashi are also here, right? I think they are doing fantastic job and manning the demo. I think they're still at the demo, I'm assuming. Okay, sorry. So let me get started with the agenda, right? So think about cloud native gaming, right? Or cloud native everything right now, right? Everywhere, the trend is to move everything to cloud, right? And imagine like gaming and you don't have an Xbox in your environment, right? You're sort of playing a game with just TV connected to some remote server and cloud, and you're doing all of those things in that, right? All of these amazing cloud everything is what I call, right? Okay. Enabling those will require sort of a new fabric of network, right? And sort of application. So how do we deploy, right? I think probably you have seen this many times, right? IoT, AR, XR, VR, right? So we actually started with something very simple, right? Okay. So the idea was that NextG networks could do really interesting things, right? And there were already open implementations, right? So this could be including low latency and high reliability. And this is like, maybe I'm just repeating the 5G spiel in a different form, right? Okay. And all of the things, great things we have seen for 5G agenda, right? Okay. So why not build one of these, right? Okay. And when we started building one of these on srsRAN, we soon ran into a lot of problems, right? And we realized that while 5G has made great advances, it's really hard to use it to make all these possible, right? Okay. So clearly end-to-end latency of 1 millisecond is really important for a lot of cloud gaming and AR, VR applications, right? But beyond that, there are also extremely different diverse metric, right? The stall of the videos, right? What is the jitter, right? All these things impact your quality of experience, right? So this is where we soon ran into, right? So the one thing, at least I'm very convinced after doing this experiment, right, is that we would need something on the edge to assist with all these applications. There is no way sort of we are going to get away with it, right? So now how do we take this all and still deliver the diverse application requirements, right? Okay. So this is where I have a second thesis, right? The edge assistance will help RAN do some cross optimizations, right? Which essentially will truly allow us to deliver these metrics and these performance, right? So how do we sort of do that, right? Okay, so these are the two concrete things, right? Edge doing everything, right? To edge departing and providing us with these metrics, combining as if need be with AI ML as needed, right? So towards this end, right, I think I don't need to say this to this audience, right? I think I'm so glad that Paul has convened this conference. So easy to talk to people, right? You don't have to say anything, right? You can just directly talk about what you really have been doing, right? You don't have to explain what are RANs, what are RICs, right? You just go there like, hey, here's what I'm doing, right? So I'm going to do the same here, right? Okay. So I'm not going to tell you anything about this, right? If I do not, please, I guess if you have questions, feel free to see me after the break, right? And I'm happy to explain, right? So I'm going to skip this, right? And okay, the only message I want you to read is following, okay? So the RANs and the RICs, right? They have different time scales, right? More specifically, right? Near real-time RIC is 10 milliseconds plus. It's sort of in the cloud, right? Therefore, there is a huge latency between when it sort of can interact, at what latencies it can interact with the RAN, right? Both in terms of getting the data out and sending the data back in, right? And I know this audience, maybe through second-hand communication or first-hand communication, have realized how hard it is to even build RICs, right? Of course, RAN itself is a really, really hard problem. But on top of that, getting all this information in 10 millisecond time second itself is really, really hard. So now, when we started looking at it, right, we did like a lot of understanding of how DU and RUs are supposed to be deployed and how CU is deployed, right? So I'm just going to show you one more picture, right? Again, no need explanations, right? But near real-time RIC will sit next to like the elements in the cloud of OCU or near real-time RIC, right? Or close to OCU equivalent, right? Which at this point within the standards, they argue for less than 5 milli or close to 5 millisecond latency, right? It never works, right? It never happens to be 5 milliseconds. It's more like 30, 40 milliseconds, but people are arguing for this architecture, right? So what it means is following, right? That if near real-time RIC has to deliver all these applications, right? Where the channel mobility is very high, right? So you cannot sort of take the information back to the near real-time RIC and get some decisions. And even if you get those decisions, those will be outdated, because your channel itself has changed by the time you get a decision back, right? So this is one fundamental issue with the near real-time RIC, right? That wireless channels are really, really rapidly changing, right? I'm giving you some time scales of what they are, right? And they are far, far lower than 10 milliseconds, right? Now you can try doing some channel prediction and other things, right? And in practice, they don't work really that well, right? Okay. Now, maybe you can prove it wrong, but here is a concrete thing that if we want to deliver on dynamic mobile links, right? Gaming, AR, VR, right? Or even sort of these contents in like in your train and cars, right? Okay, we need to handle these dynamic mobile links, right? So that's first problem, right? And this is where near real-time RIC will fail. And you can see now the wired connection fails. So wireless, I think we cannot much. Okay. All right. So this is where we thought we'll come up with something cool, right? And before we come up with cool, we also tried making work with the near real-time RIC. It failed, and I'll show you some real-up data and experiments, right? So we argued for something called real-time RIC. I don't know, my mouse pointer is visible? No, it's not. Okay, you can see there, right? Yeah, you can see somewhere hovering this red thing, red real-time RIC, right? The idea really is that it sits right next to the DU, right? And it imparts intelligence to DU to do some optimization, right? And it essentially can abstract out all the data from the DU and then send its policies and decisions back to the DU, right? Truly, it sits on the edge and provides you intelligence, right? And you could have all DU, CU, and all the way up to first step of CN here. And it can also still extract all that information and impart intelligence back, right? And I'm proudly can say that this was built first on srsRAN, right? So I'm glad about that. And thank you, Paul, for that invitation as well. So the first concrete point then is that, let's say if we build this RAN, right? Okay. Now I have to deliver content or some of these applications I told you about upfront, right? Okay. So the problem with the applications, right, is that if you don't know about the state of the application, right, or where it sort of starts or where it is, like, for example, if there is a video stall upcoming, right, okay, how do I know about this user is going to run into some problem, right? Okay, so how do I do resource scheduling with awareness of application, right? This was the second problem I ran into, right? Because without knowing that, you can't deliver some diverse application related metrics, right? So second thing, we had to somehow figure out a way to get even this application awareness within our sort of this real-time RIC, right? So this is where the final architecture is, right? Okay, I'm gonna maybe now take some time and explain. I know this might be, it's not really that new, but it's still, there is some additional things, right? So we have our real-time information exchange system, right? Okay, I'm gonna hover over here, right? Okay, so you know the RAN elements, all of us, right? And then there is near real-time information exchange, and it goes on to feeding near real-time and sometimes non-real-time, right? And there are different, I'm just simplifying this diagram a little bit, right? To help us, right? Now, there is a real-time information exchange, right? Which takes information out of DU and even other layers if you need to, but we rely E2 for the others, right? This is, we call it real-time E2. And it's really, really challenging to get something very interesting and useful within a very short time frame. So we get a lot of this data back into the EdgeRIC, right? In EdgeRIC, you can run something called RT apps, right? Or we also call them micro apps, right? Because they are running at microsecond latencies, right? And once you have those decisions back, you can send those back to the DU, right? That's first aspect of this. The second is, it sort of gets in a some non-trivial way, some application state information as well, which is sort of delayed, right? But besides that, everything else is really, really very quick and fast, right? And I'll go over some of the numbers in more detail. So one, we are application aware. Two, we can handle dynamic environments because we are really operating at very, very fine time scales, right? And I guess I will just say this is more on Paul, not on me, right? We are ORAN standard compliant because Paul is ORAN standard compliant, or at this point he is now, right? Okay, and not to say Paul, it's the entire SRS team, right? So what did we do first, right? So first we took an application and we tried to train a reinforcement learning with near real-time RIC and EdgeRIC, right? So near real-time, as you can see, it's a very stable training. The problem with the near real-time, non-real-time is that it's unstable, or near real-time rather, sorry, not non-real-time, near real-time. Even with 60 millisecond, and we have tried at much lower latencies, it's always unstable, right? So truly, like, if you get even a good performance in a short time, it's not a consistent performance you get delivered, right? Okay. So this is the key application we tried to build first and the foremost, right? And by no means, this is the only thing. We have released this platform just this week, right? Okay. So you can go try it out, right? But the idea is that you can do everything from Phi, Mac, RLC, all the cool optimization you want to do, right? Go ahead, go nuts, right? We want you to try all of those, okay? So what is it we can do, right? What we can do is that think of RAN stack as an environment, right? Okay. We can take all the states you want, right, by simple hooks into the EdgeRIC, right? And EdgeRIC is tied up with nicely with OpenAI Gym. I don't know how many of you know about OpenAI Gym. Sort of think of, it's like a ORAN of AI, right? Okay, that's OpenAI Gym for you, right? Okay, so once the information is within OpenAI Gym, you can do a lot of cool machine learning algorithms and ideas as you want, right? And if you don't want to do machine learning, you want to just do simple stuff, right? Even that you can do here, right? Okay, it just gives you a Python environment. You can write anything in a Python environment, right? Get back actions, and those actions are then fed back in real time to the RAN stack. The only caution we have to do is that we need to make sure that your RT apps or micro apps or your Python codes, their execution times are in sub microseconds, right? Or not sub microseconds, but tens of microseconds, right? So that we are able to give consistent performance back to the RAN, right? So that's sort of the key thing, right? And believe it or not, right? I think the people who have tried implementing, right? It's really, really hard to get these numbers down into microseconds when you're trying to get information out of RAN stack and then feed back decisions into the RAN stack, right? It sort of people struggle with hundreds and like milliseconds or like tens and hundreds of milliseconds when they are trying to do these type of things, right? So we did a lot of low level programming, and this is where Wuyun and Ushashi has spent really, really lots of months on debugging every single thing out of the stack, right? And figuring out how to do it, right? And we chose to show a scheduler because we still strongly feel the way to deliver application level metrics at a first scale, right? Is that you somehow have an app awareness. And in addition to that, if you do scheduler reasonably well enough, you could get a lot of application level optimization going for you. That's why we started with the scheduler. So to be more specific, we take the information from RAN stack between all these three layers and the application layer state, which comes back. And we run the execution of the policy within the real-time RIC and give the decision back. And those decisions then are used by RAN stack to do RB allocations, right? I'm going to be specific now, and I can be specific to this audience as I keep praising the audience. It's awesome, right? So now the goal is to do QoE optimization, which is quality of experience, right? Okay. I think we have all heard of quality of service, quality of this, quality of that, right? Just maybe I'll take 1 minute and say what quality of experience. It's more of user level behavior and understanding, right? So for example, right, something none of our 5G, 6G standards cover is, for example, jitter. Jitter is a very important metric whenever whoever knows video streaming, like you talk to Sony gaming or other gaming platforms, they know exactly when somebody's talking about jitter, they're like, oh, awesome, you can optimize jitter, that's awesome. So the concrete point I want to make is following, right? That these metrics are not considered when we are designing our 5G, 6G standards, right? We consider throughput, we consider latency, we consider millions of users per cell and so on and so forth, right? We need to transcend beyond that and start thinking about these applications and delivering this, right? And it's not just video streaming, right? Everybody has different metrics, right? Okay. You heard Scott yesterday talking about all the tactical awareness and when and where, right? And there are like these different applications sort of being enforced here and there, right? So now the way we'll go to more specific here is that the RAN state goes into the GIN. You can train whatever policies and give back weights for specifically in this case, we just chose weight as an abstraction of the information coming back from the EdgeRIC, right? Now, not only that, we can log a lot of information from the historical information in the RAN stack and send that information in near real-time RIC. And you can use that awesome compute the near real-time RIC has, right? And all this historical information to train new policies, right? And these policies can be to optimize jitter, right? And give that policy back to the the RIC, EdgeRIC, real-time RIC, and it can keep executing those in real time and giving the performance your RAN stack needs, right? So that's sort of how this all works, right? Okay. So I'm gonna skip few slides and just maybe go to this slide, okay? So actually, I think I'm gonna running behind in the time, right? So looking at this, so this is really how the overall operation works, right? In a more detailed form, right? All of our RAN state information is logged in the data logger as well, right? And they also go to the real-time RIC, right? So which is the execution module here, right? Which keeps executing policies and returning back the actions back to the RAN stack, right? And it operates in a perfectly decoupled fashion to the RAN stack, right? So imagine if our EdgeRIC goes down, that doesn't mean that the RAN stack will go down, right? It's designed in a way that it's perfectly decoupled from RAN stack. And even if it dies, the RAN stack will keep operating on its own, right? Without sort of waiting for EdgeRIC, right? So it's designed in a way where it doesn't wait for the RAN stack. RAN stack never waits for the RIC. If it gets a decision from RIC, it's good. If it doesn't get a decision, it will just operate on its own, right? So this really a resilience is built into the system, right? Now, in this specific case, the information goes out, execution of policy takes place, and the policy returns back with a weight. And what we found very interestingly is that you can use weights as a very simple abstraction for doing all reinforcement learning optimization. So this is the second message. If you are trying a lot of RL things, we are just running a proportionally fair scheduler in the RAN scheduler, and weights can do every policy we have tried, it can do and attain those, right? And Srinivas is working towards proving if it's optimal as well, right? In theoretical framework as well. So let's look at more detailed execution. And all of this is implemented using ZMQ. It's implemented using ZMQ, the information exchange, and there are simple hooks you can attach, right? And if you want new information, you just write one few lines of piece of code, and you build your stack, and it bring it up, and it will start dumping that information, right? This is the overall flow of this, right? Okay, and I added this slide because I know this group can get it really well, right? I added a few more extra slides just during the lunch break because I've been having so much awesome discussion. I thought we got to go in more details and explain everyone what we are doing, right? Okay, so start with step 0 where RAN measure the states and RAN transmit. So a lot of asynchronous operations are what you see here, right? The first observation, you should make that, right? And the reason, and this is just shows truly why it's built in this way, so that you can have a decoupled operation of RAN and RICs, right? So your state measurement goes parallelly to the RAN's execution, right? 5, 6 are RAN's execution, if you see, and 0, 1 is RAN's transmission of states, right? These are perfectly multi-threaded operations which are taking place, right? And RAN never waits for RIC. If it gets a decision from the previous time frame, it will use that decision. If it doesn't get it, it will just continue as if nothing has happened, right? So this is the one key thing which allowed us to get to really, really microseconds of latencies, okay? Right, that's it, right? I think, and if you want, we can dig deeper, and the paper is already out there. If you search EdgeRIC, you'll find the paper. So there is another interesting thing which we did for synchronization on how do you do TTI level synchronization, right? And again, you can read more details in the paper, right? Okay. The key abstraction is the decoupling, which allowed us to get to these microseconds, right? So let me show you the performance, right? Even if I'm dumping 90 UEs information, right? And imagine we are operating at a TTI frames, right? Every milliseconds, you don't have more than 100 users ever, even in the production level stack, okay? So 90 users, we can dump all their state information without getting even beyond 50 microseconds, right? So this is really the coolest result I have seen, or at least I found, right? So in 50 microsecond, we have exchange of information going to the RIC and coming back. It's a round trip, right? Okay. And we show on x-axis with number of users, to y-axis the number of what is the performance in the median level, right? So as I enforce this, and then we tried executing some really complex policies in the RIC and getting their results back. Even there, we were getting to 0.1 millisecond, right? So in 100 microseconds, we were sending information, getting that computed, and getting those decisions back into the RAN, less than 100 microseconds, right? Even if we had 5G FR2, this would work, okay? Because in 5G FR2, the TTI drops to 125 milliseconds or 125 microseconds, okay? So any case, I'm gonna now go over some first, let's see if in synthetic world does it work, right? What I mean by synthetic world is that we instantiate everything. The channels basically just take the IQ samples and directly feed it to srsUV, right? Okay, and now, as I said, this audience is awesome, right? I don't need to explain anything. Okay, so going back to this, right? And then we instantiate EdgeRIC on top of this, and we have basically 4 users, right? And we take and play some different channels for each user, and then we just sort of have this scheduling weights coming back, and all the information of backlog buffers, RNTI, CQIs, all of that going into the EdgeRIC, right? Okay, and keep getting back decisions, right? We run all of this as a single container, right? And let's say I synthetically created this CQI, right? There are 2 users, okay? Once they're asymmetric, right? One's channel is good, other's channel is bad, right? Okay. Now, this is really, really designed to perhaps make near real time look bad a little bit, because it will operate at a certain delay of this channel, right? And therefore the decisions they give us will be bad, right? Okay. But we just wanted to stress test our system and see if there are any benefits of doing EdgeRIC, right? So now the thing you need to see is following, right? If my channel is better, I should get more slots. Okay. My channel is bad, I should get fewer slots, right? Because that will overall aggregate maximize my base station's throughput, right? At this point, that's what we set as a target. So in the EdgeRIC, the weights track the channel, okay? The red tracks the red here, okay? Here, the red doesn't track the red, okay? It's worse, right? Whenever red's channel is really good, it gets the fewest amount of resource block, okay? Right? It's like really created bad channel for our EdgeRIC to shine truly, right? Okay. Now, in the shining case, it shines, right? But not only that, it just shows that our execution works really. Okay, once again. Sorry, I think I need to be very careful when I touch this, right? Okay. I'm going to just hold this myself and hold myself down here now. Okay. I'm creating the vibrations. Okay. So, and we show system throughput, and this is shows at least like whatever 10% improvement in throughput, right? But throughput really is not our key abstraction. We just wanted to see if there are some benefits to doing all of what we are doing, right? Okay. So let's go to the real world evaluation, right? The problem we ran when we started doing over the air channels is that we tried training models over the air, they never stabilized, right? The problem is that from one instantiation of the experiment to the next instantiation of experiment, the channel is entirely different. And we just start from a point where it doesn't really make any more sense for it to continue to train. So how do we get repeatable training, right? And second, even if I somehow synthetically create that repeatable training, how do I make sure that will translate to the real world improvements in throughput, right? So we spent like, hey, there's a lot of digital twin activity out there. Let's try that, right? Okay. And as usual, like everybody else, we started with MATLAB channels, right? By the way, don't use MATLAB for your digital twin ever, okay? Right? And it never works, right? Because they don't have space-time consistency in the channel. I'll talk about that in a minute, right? Now, the idea really was that we used MATLAB, it failed. Then we went to Wireless Insight. We were doing a lot of channel in digital twin estimation and like running a simulation of this, right? We sort of created our outdoor test bed in our digital twin with few buildings we could do, right? An experimental setup. So this is a UCSD road. It's a Atkinson Hall and a few other halls. I don't know if you know of it, right? But basically the hope was we have these and we have a lot of open source 5G. And in specific, srsRAN is what we have heavily being used, right? So can we replay those channels and train the entire EdgeRIC and the policies and all of it, right? So turns out if you use MATLAB, there was a problem. Even the 3GPP channel implementations are bad, by the way, right? Okay. So here's what you have to do. You have to basically create space and time consistency, right? The problem is that like when you use all these simulation channels, the user jumps from one location to the other location, right? And when you're trying to train something which is trying to learn some underlying behavior, it cannot learn that. So this is where we realized this is where a lot of these simulated channels were failing, right? So we created something called space and time consistency in the channels we were simulating, right? It's not really earth shattering, but it was at least some interesting things which actually made all of our training really work. So then we used Wireless Insight. We had created users, cars, and they were running around, right? And they were collecting different channels. All that channel we can just sort of captures as a ray tracing models and diffractions. And once you have those, you can replay those in your simulation, right? So here's how I can show you some instances of channels and how this is a car like running around and I'm showing you all the channels overlaying. And we also had SDR based channel measurements, right? I think there are a lot of channel measurements, I want to say, even in powder at this point, right? We can use those as well for your experiments, right? So we did ourselves, right? And we have our own FR2 phase array millimeter wave test bed as well, right? I think it's actually the only one programmable FR2 out there right now, okay? So if you want to try that out, email me as well, right? So we collected a lot of channel, focused on FR1 at this point. What is the idea? The idea is to apply the space-time consistent channel. So this is emulated base station, which is nothing but basically your srsRAN, right? Applying channel and you're getting different users and their channel between them, right? And this can be your Wireless Insight based channels, or this can be USRP based over the air traces collected, right? So we can take all of those channels and replay those channels in here, right? And I can just show into more details how this is implemented. Okay, yeah, we are back. Okay. I'm going to really stand this time around, okay? And try to look at my small screen on small slides and see what's going on, okay? So Yeah, okay. I'm almost there, done. So basically we have a ZMQ based GNU radio block, which can essentially create multiple channels, and each channel can be associated to use each user, right? And you can replay all these, and you can instantiate as many users as you want, right? Okay, and you can run an application client like a video streaming or whatever you like, right? And all of that state and information then is going to the EdgeRIC as well, right? I know this figure is slightly misorienting based on the previous slides I have shown, right? But just hang on and try to continue with this. In addition to that, we have a lot of indoor test bed. This is my lab, right? We have a lot of indoor 10 plus SDRs, right? Which is hanging in the roof, right? And all of them are placed at different locations. This is the floor plan map. We have an anechoic chamber. We do a lot of experiments there as well, right? So we have like any SDR connects to this entire network. We have an octoclock reference to each of them. We have Cisco high-end switch, which essentially we have 10 plus SDRs, all of them network connected to the Cisco switch. And then we also have some different types of monitoring and spectrum observability radios, which are SM200 signal hounds, right? And then these are all connected to high-end servers, and all of this data is collected on indoors, right? And you can make any user, any base station, and collect lots of data. Again, if you want to try it, just email me. Happy to make this available to all of us. Okay. Now, second, Srinivas and their team has this called Realis testbed, which also will be soon available to the larger public. This is funded by State of Texas. It's innovation proving grounds, right? They have a lot of disaster city, lots of cool outdoor settings, right? Where you can do a lot of experiments. They will plan to have a lot of research base station and some commercial base stations as well. And you can connect to any of those and do a lot of experiments and data collection, right? Okay. I'm going to skip since I have only 2 minutes, right? And these slides, everything, I'll make sure to email it to Paul and he can share with the larger audience. So we did 4 types of data collection. We have a turntable where we placed a B210. We did a car-based B210 experiments, right? Drone-based, mobile robot-based. We collected lots of channel measurements, right? And all of these were recorded, then used in the digital twin to train policies, right? And here's how our training curve looks, right? It's look pretty good actually, right? And if you have seen our demo, you can see even if you use an intermediate policy, which is not fully trained, that has far lower performance to the end-to-end, right? And we were able to evaluate in real world, and it shows that reinforcement learning beats max weight and max CQI, right? In throughput. By the way, throughput is not the important metric out there, right? I'll show you some really cool demo now. Next up, we basically try to deploy, and I'm going to skip some details, but for a video streaming, right? Okay. And one thing you can see in this video, hopefully this video is large enough, right? Is that first we are running with max CQI, right? Policy, right? And the problem is that every time buffer drops below 2 seconds and it re-triggers and it creates stalling events in this, right? But then now we deployed our reinforcement learning, and the demo will start playing a reinforcement learning scheduler, right? And play the same video again. And I think if it's observable, there is an observable difference. Our buffer never goes below 2 seconds, right? Immediately our reinforcement learning catches up and it re-triggers everything, right? So it shows that in real world streaming as well, we have much better performance, right? And I will give you some quantified numbers, right? So this is our reinforcement learning showing the stall durations, right? Our stall durations are much lower than the popular max weight and max CQI. It's an application aware, and we have significant gains because of that, right? And I can show you in more details, but the concrete thing is that we have 3 times better performance in comparison to this. And you can do a lot more applications, right? And I'm gonna maybe finally turn to this interoperability lab. We have a lab, as I was saying earlier, right? We can connect to Science DMZ. So the setup I showed you of our facility, it's essentially connected to Science DMZ network. So we have deployed 2 Gnode B, one in NYU, one at our labs, and we can connect those 2 Gnode Bs, and we can truly run a lot of UE experiments here and there. And we have ran a lot of traffic experiments from here to there, right? And soon we will have also Trellis or the Realis testbed within Srinivas's lab connected to this setup as well. Now, this is a national research platform, by the way. You can go there. It's like an AWS of its own, right? If you're running out of your compute resources, just come to us and I will hook you up with this, right? You just need an NSF project funded. And if you have an NSF project funded, you can use all of these facilities, right? So there are 7 locations, which has really large number of servers. In total, they have 4,000 nodes, right? And these nodes are like really at least 8 GPUs each node and so on and so forth, right? Really powerful nodes, right? Again, I can show you a bunch of, this is in Nebraska, this is in a bunch of other facilities, and this is San Diego Supercomputing Center, right? This is what our facilities looks like, right? So all of our SDRs with a switch are connected to this facility, right? And this is the countrywide network and how it sort of works and operates, right? It has all the cool gadgets, right? From Kubernetes to Helm charts to everything you can imagine, right? Because they are basically running their own AWS. So you could also get resources, right? No industry though, right? Okay. Any case, so, and I think I will maybe save some time and not go into details of this, but basically you can run a lot of experiments here, right? And it's a large test bed. As I said, the key thing is that our sub-millisecond travel times from east to west coast, right? And very, very high data rate, right? And if you have DOE and DOD generally are at some endpoints hooked to this as well. So they can also come onto this network if they can figure out the paperwork on their end, right? Okay, with that, I'm happy to take questions.
Thank you very much, Dinesh. As we're running a little bit over time, we might leave the questions. Dinesh has a demonstration with his students down in the hospitality zone, so I encourage you to seek him out and have a discussion.